Welcome to the SOFLUX webinar today. First, I want to make a few announcements about SOFLUX. SOFLUX is the Southern Ocean Airsea Flux Working Group, and we have initiated a webinar series which is nominally monthly. There won't be a webinar in August, but in September, we're expecting to have a webinar on the Polar Pod program. We welcome volunteers to speak in coming months, and the schedule is intended to be highly flexible because of the number of time zones. So we've made a commitment to record the webinars and to make the recordings available so that we can accommodate speakers when they're at a time of day when they can be coherent and that other people can catch up when they need to. Today, we're really fortunate to have Alison Gray, who's an assistant professor at the University of Washington. She's done extensive work with the biogeochemical Argo float program in the Southern Ocean, the SOCOM project, and she's going to talk today about some of that work on Airsea CO2 fluxes in the Southern Ocean. So welcome, Alison. Thank you for joining us.
Thank you, Sarah. Yeah, and thank you to all of you for watching either live or later on, and thank you to the organizers for inviting me to give this webinar. So yeah, so as Sarah said, I'm going to be talking today about Airsea CO2 fluxes inferred from BGC data, BGC Argo data in the Southern Ocean. There are floats that are starting to become more and more available, and data is becoming more available from other parts of the world from similar profiling float platforms, but I'm not going to talk about those. I'm really going to focus on the Southern Ocean here. And I want to acknowledge, before I start, the significant and fundamental contributions from the people that you see here listed, especially Channing Friend, who's a graduate student at Scripps, as well as Seth Wyszynski, Nancy Williams, and then all of the SOCOM PIs and exec. And then last but not least, I want to thank, of course, the funding agencies for supporting SOCOM and the biogeochemical Argo in general. Okay, so I'm going to start actually with my take-home message, just in case, I know in this day of watching online seminars, it's gonna be a little easy to zone out sometimes. So I thought I'd just really start with what I want to make sure that the message that I get to you today, which is two things. One is that biogeochemical Argo floats really offer a great way to improve our estimates of Airsea CO2 fluxes. And mainly this is done because they're expanding our observational coverage in space and time. And that's really valuable when we're thinking about, especially some of the sparse sort of nature of shipboard observations. But the flip side of that is that there is a larger uncertainty in these estimates from floats than we get from our shipboard data. And, I think some of that's inherent in how we're doing the measurements. I won't go into all of this, but there's a lot of room for improvement. I think if we can make better estimates of of the sort of marine inorganic carbon system, then and refine our understanding of some of those sort of theoretical constraints on how carbon behaves in seawater. That will really allow us to refine and really expand the use of these float data. Okay, and then the second main point that I want to leave you with today is that the float data that we have already, the observations from the Southern Ocean Carbon and Climate Observations and Modeling Program, or the SOCOM project, we have a number of years of data already, and this has revealed some really interesting things that we maybe weren't as aware of as before, which is that there's appears to be a significant outgassing of CO2 in the high latitude Southern Ocean, and it's really seems to be coming mostly from the Indian and the Pacific Ocean in wintertime. So I'm going to go into all of those sort of more detail into both of these points, but I just thought I would start with that so you can know where we're going. And also, if there's any questions or anything, feel free to interrupt me. I'm not sure if you guys normally take questions through the chat or what, but maybe Sarah can interrupt me if there's something.
Yeah, anything in the chat, or I think we're a small enough group online that we can interrupt if we need to.
Great, thanks. Okay, so before I really get into any details about BGC Argo floats and how we're using those data, SOCOM data, to estimate Airsea CO2 fluxes, I just thought I would back up and say that, you know, why do we care about Airsea CO2 fluxes in general? One of the main reasons is that the ocean has played and continues to play a really important role in taking up anthropogenic carbon that we're adding to the climate system. So in this plot from Friedlingston 2020 in the global carbon budget, you can see that these sort of arrows show the cumulative change since 1850 in the anthropogenic carbon cycle, as well as the mean fluxes over the past decade. And in both of these, the ocean component, this sort of darker green part, makes up about a quarter of the sink of anthropogenic carbon. And so it's playing a really important role in that sense. And of that quarter of the ocean's CO2 uptake, 50% of that, more or less, is actually being taken up by the Southern Ocean. So that's why it's really important if we're, you know, we want to understand future changes to our climate system and what's going to happen as you know, as time goes on in this experiment that we're doing with perturbation to our carbon system. We really need to know what's happening not only in the ocean, but also in the Southern Ocean. And so these plots here are just showing on the left-hand side from a model-based study from Frolicher in 2015, the cumulative anthropogenic CO2 uptake since the beginning of the industrial era. And you can see in these red colors that show all the uptake, the Southern Ocean really stands out. So it's a place where anthropogenic CO2 is entering the ocean. And then you know, so far I've been talking really about the anthropogenic CO2, but when we actually go out and make measurements in the ocean, we're really measuring the total CO2, so both the anthropogenic component as well as the natural carbon cycle. And that total Airsea CO2 flux is what's shown in the plot on the right. And this is based on observations from Lanchitzer et al. In 2014. And in this plot, the outgassing is shown in red, so opposite colors. But the point here really is that the Southern Ocean, again, shows up as an area with significant uptake of total CO2, shown in the blue colors here, as well as some outgassing in the more high latitude part. So, you know, we know that the Southern Ocean is an important region in terms of the global carbon cycle. And one of the reasons that is the case is that there's because of the circulation of the Southern Ocean, it causes there to be a very unique sort of set of circumstances in terms of the carbon cycle. So this is kind of illustrated very nicely in the schematic from Gruber et al. 2019. And I'll just kind of walk through it quickly. I'm sure most of you are familiar with the Southern Ocean circulation, the circulation of the Southern Ocean. And you know that the upwelling of sort of circumpolar deep water that's occurring here in the along the ACC, which is shown kind of by these black contours. This upwelling of circumpolar deep water carries with it so we'll focus on first on the natural carbon. It has very rich carbon, natural inorganic carbon. So this is DIC that has been this water mass has gained as it's traveled around the global ocean, and organic matter has rained down into it and been remineralized. And so when this deep water reaches the surface in the Southern Ocean, it leads to this natural outgassing of CO2. And then as that water moves both to the south and gets subducted, gets transformed into Antarctic bottom water and then sinks and moves out of the Southern Ocean as Antarctic bottom water, carrying carbon with it in exporting carbon in that sense. But some of that water also moves to the north, and this water, in addition to being enriched in this natural DIC, has a lot of nutrients, and that high nutrient load, as well as thermodynamic changes associated with warm water traveling south, can lead to a large natural uptake of CO2 in the more sort of north of the ACC and the more sub-Antarctic waters. And so this natural carbon cycle, which consists again of the outgassing of CO2 in the more high latitude Southern Ocean, and then the uptake of CO2 in the more northern part, are sort of best estimates based on shipboard data and models and such, sort of give us approximately a net neutral effect on the total CO2 uptake. So that natural carbon cycle, at least in this Gruber paper, was estimated to be about 0. But superimposed on top of this is this anthropogenic uptake, which is also due to the circulation bringing this deep water up to the surface, and this deep water, although it's enriched in natural carbon, hasn't been in contact with the atmosphere for many hundreds of years, and so it has negligible anthropogenic CO2. So that is shown in this plot on the left, the sort of anthropogenic CO2 distribution. And so when you get when this water reaches the surface, it can take up a lot of anthropogenic CO2. So the total effect is that our contemporary estimates of the CO2 flux in the Southern Ocean are approximately 1 petagram of carbon per year of uptake. And it's really the sum of both the anthropogenic and the natural components. Okay. However, that picture is still a bit uncertain. So our observation-based estimates of the Southern Ocean carbon flux, I would say, are still fairly uncertain. And that is shown really nicely in this paper, in this recent paper by, I'm not sure how to pronounce the last name, but Gloji et al. In 2021, and where they did a very thorough analysis using models and then sampling the models where the shipboard observations are, which you can see in this panel B is an indication of the shipboard distribution for CO2, PCO2 in the surface ocean. And it's colored by the number of months of data in the SOCAT database. And then they use that sort of synthetic subsample model and along with the sort of one of the standard methods we use to reconstruct CO2 fluxes from the shipboard data, which is the self-organizing map method from Lanchitzer et al., or the neural network. And so when they reconstruct, by using this in a model sort of simulation, they can compare the true carbon flux with what the reconstructed carbon flux is. And the bias is shown in this top panel here when they do that. And you can see that the Southern Ocean really stands out as an area with some of the largest biases in the annual mean CO2 flux that's been reconstructed from the shipboard observations. And that's really not a surprise. If you look at the distribution of the shipboard data down here, you can see that the Southern Ocean also stands out as a place with fairly low data coverage. Okay, so not only are our observation-based estimates of the CO2 flux in the Southern Ocean fairly uncertain, it's also a place that's very difficult to model. And so this plot is taken from a recent paper by Hauk et al. Looking at the ocean biogeochemical models used in the global carbon budget. And this is specifically, this plot is showing the natural Airsea CO2 flux in those models. And you can see, basically, if you look at the Southern Ocean, there's a lot of variability from one model to the next. And that's kind of captured in these bar graphs too, where if you look at the 44 to 58 south and then south of 58, you can see that there's a lot of variability, not only in the strength of the CO2 flux, but the sign. So some models show a lot of uptake, positive numbers here, and some models show net outgassing. And this is, again, for the natural CO2 flux. This is not the anthropogenic part. And so there's a lot of uncertainty in terms of exactly what is going on. And this is just the annual mean. The Southern Ocean also stands out in both of these papers in terms of a place where we're not constraining the variability very well. And one of the reasons, like I mentioned 2 slides ago, that it's so difficult to constrain the Southern Ocean CO2 flux is really our lack of year-round observations. And so this is another way of looking at the plot I just showed, but kind of breaking it down by decade. And this is, again, the number of unique months in a 1 degree by 1 degree box sampled by the shipboard PCO2 database, or SOCAT database. And these data are very high quality. It's an enormous resource to have all of these data together. And it's really kind of enabled such an amazing transformation in our understanding of the CO2 cycle in the surface ocean. But I would say, because it's based on shipboard data, it's really lacking in terms of its seasonal coverage in the Southern Ocean. And so outside of Drake Passage, which shows up as a place with a lot of data, and maybe some near New Zealand and Tasmania, there's really only summertime data in the Southern Ocean, which isn't going to probably surprise anybody here. Okay, so that's where SOCOM and BGC Argo in general can come in, because biogeochemical Argo floats offer a really fantastic opportunity to observe the oceanic carbon cycle with amazing coverage in space and time that you just can't get from ships. So this is, was recognized as sort of one of the founding motivation for the SOCOM project, which started in 2014, deploying its first BGC floats. And these are, regular Argo floats, except with the addition of measuring oxygen, nitrate, and pH. And
maybe monitored.
Okay. And also some bio-optical variables as well. So this plot is showing just as of yesterday what the distribution of the SOCOM floats look like, where so the dots show you the current or the last known location, and then the black tracks show you the trajectory of the floats since their deployment. And so I'm going to tell you about how we use these float data to estimate Airsea CO2 fluxes. And but again, kind of starting with the punchline a little bit here, this plot is showing those Airsea CO2 fluxes estimated from the SOCOM data from 2014 to 2020. So this is a plot made by Channing Prend in this paper that is in review right now. But you can see, there's a lot of variability, both spatially, and then the time part is not really sort of represented here, but just to kind of show you, kind of the end result of what it looks like when we calculate fluxes from the float data. And how do we do that? Well, the Airsea CO2 flux here, F is the product of a gas transfer velocity, solubility, K naught, and then the delta PCO2, which is the difference between the ocean PCO2 and the atmospheric PCO2. And in this study and in previous works, myself and other people have used this Wanikoff 2014 parameterization for the gas transfer velocity based on a squared wind speed, and I used wind speed and sea level pressure from ERA 5, but That's not really particular to the floats, that's similar methods or products are used for pretty much most these bulk formula-based ways of calculating Airsea CO2 fluxes. So I'm not going to really focus on that part. But what we are getting from the floats, what's unique that's coming from the floats is the PCO2 in the surface ocean. And so how do we get this float-based PCO2? We're not measuring PCO2. If you were listening carefully, or if you're familiar with the float data, you know that I said we're measuring oxygen, we're measuring nitrate, and we're measuring pH, but we're not measuring PCO2. Luckily, we can use this pH measurement to calculate PCO2. And but first, I just want to show that the floats are measuring pH, and we're doing a pretty good job. So this is an update from Ken Johnson's 2017 paper, but it's comparing float pH to bottle pH. And this is when we deploy the floats, we also take a high quality CTD cast at the same time. And then those data are not used to calibrate the floats, or they're only used to validate. So this is what's shown here is that validation, and you can look at both the sort of a scatter plot and as well as the difference, a histogram of the difference between the bottles and the floats. And there's a small mean difference, but overall is pretty good. So we're measuring pH. We're doing a pretty good job of it. And then we also are measuring temperature and salinity from the floats and have a regular CTD on them. And then we can estimate alkalinity. And we, based on the other things that we're measuring, temperature, salinity, oxygen, nitrate. And we can do that estimation using algorithms developed by a number of different people or groups. This one is the locally interpolated alkalinity regression from Carter et al. 2018. We can use other methods of estimating alkalinity to get a sense of the uncertainty that's introduced by that estimation step, but it's really not the largest source of uncertainty in this calculation. So we feel that especially when you use pH and alkalinity to compute PCO2, the variability in the PCO2 is really largely driven by the pH. And so because that's our measured variable, we feel pretty, feel that this is a pretty sound method. But it's not without uncertainty, and that's certainly important to note that there is, because we are not directly measuring PCO2 like the shipboard instruments do, we are estimating it, and so we really need to make sure that we're accounting for the additional uncertainty that introduces. And this plot or kind of schematic is there's a lot of stuff on here. I'm not really wanting to try to understand all of it, but it's from Nancy Williams' 2017 paper, where she does a really thorough job at looking at all of the different sources of uncertainty that go into how the float pH is calibrated, how it is adjusted in real time, the algorithm alkalinity estimates, and then as well as the calculation of PCO2 from pH and total alkalinity. And I want to kind of note this one in particular, that the uncertainties in the carbonate system equilibrium constants is I think there's coming, not just this study, but a number of studies that have come out over the past few years that have really looked deeper into the carbonate system consistency, and there's a lot more details there than I probably can do justice, but essentially there are some uncertainties involved in this calculation that come from not knowing the equilibrium constants as well as we'd like. And one of the sort of ways that the float, one of the, I guess, consequences of this in terms of dealing with the float data and trying to estimate PCO2 from float pH and estimated alkalinity is that we need to do this bias correction. That is a pH dependent bias in the pH that has to do with how you're calculating, is only used when you're calculating PCO2 from the pH. I'm going to refer you to Nancy's paper and others for more details, but the point being is that we think we're doing a pretty good job after this bias correction. It seems if we do sort of a top-down uncertainty estimate where we compare the float PCO2 to the shipboard PCO2, and it seems that there is a bit of a mean offset, but it's about 4 microatmospheres, which is less than our total uncertainty. So, you know, to sort of reiterate, the main point there is that there is likely some, or possibly some bias, we don't know, or else we would correct it, but there's some possible bias in the float-based PCO2. We don't think it's, you know, too big, but we do want to be careful to take that into consideration when we're using the data, especially when we're computing the uncertainties in our float-based estimates of CO2 fluxes. And not only that, but I think there's some room for improvement here too, which I'll talk about in just a second. But before I do that, I did want to mention that the floats are also, you know, the floats are sampling every 10 days. So there's some concern that, oh, well, Airsea fluxes, you know, there's a lot of rapid variability. Are we missing some really important components of the variability by only sampling every 10 days? And so Seth Bushinsky in 2019 looked at this issue, at this question in detail, and found that if you, you know, if you look at a mooring and you subsample like the floats would, you don't lose, if you only do a 10-day subsampling, which is what the SOCOM floats typically do, you actually don't get too much bias in your estimate. So we feel pretty confident that this 10-day sampling frequency of the floats is not the largest source of uncertainty, at least. But again, coming back to those uncertainties in the carbonate system equations, there's been a number of papers in the past few years, some of which I've listed here that have kind of are delving into this. This plot came from a recent paper by SOFLUX et al., and it specifically looked at the SOCOM float data and the effect of the dissociation constants, and if using a different set of dissociation constants, particularly at cold temperatures in the Southern Ocean, where we in the high latitude Southern Ocean, where we find very cold temperatures, it resulted in a pretty significant difference in the PCO2. So I think this is, I'm not trying to say this is correct versus other sets of constants, but there is, I think, a growing awareness in the carbonate community that this is something that we really need to get a better understanding of. And I really hope that people are and the funding agencies are taking that on, and that we can make some significant progress in this and reduce our uncertainties. We can go back and recalculate all of the float data with new constants. So it's really, I think, promising as a way to reduce our uncertainties in the float-based estimates. Okay, so I'll go back to sort of my second main point. That was my what I really wanted to say about sort of how we calculate Airsea CO2 fluxes from floats, and both the benefits and sort of the caveats of doing that. But then, you know, given that we're going to use these data to estimate Airsea CO2 fluxes, what can they tell us about the Southern Ocean in the past 7 years or so? So this, again, is just showing all of the float-based flux estimates over that time period in the Southern Ocean. But if we kind of group those flux estimates together and do some averaging, both seasonally as well as or annually, as well as in space. So you can see these black lines, which I'm sure most of you are familiar with, the Airsea fronts, and this, but essentially these are the various fronts of the ACC, and the subtropical front appear determined by using the Airsea criteria on a more updated temperature and salinity climatology. But essentially, what we first started out doing was taking all those float data, which again, I'm just kind of showing here now, separated into those different regions defined by the fronts in the ACC. So the most southern region here would be the sea ice zone. So this is the floats that are actually under sea ice for part of the year. And then moving out to the north in the Antarctic southern zone. So the sort of the second, the sort of more southern half of the ACC, and then the polar frontal zone. So if we separate the floats into these zones and then average them, we can come up with an annual net CO2 uptake in each one of these zones. And so that's what I published, some estimates based on the float data in 2018. What I'm showing here is an update of that to include more data that, so that a paper that came out in 2018 was based on only 35 floats that went through 2017. And now I've updated this, and I think it includes now like 90 floats and data through the end of 2018. But the picture is actually not very different compared to the earlier study. You still find that the floats more or less agree with the shipboard data, shipboard estimates in the subtropical region, but as you move further towards Antarctica, you get a larger and larger disagreement. And in particular, the Antarctic southern zone, we see a really strong outgassing in the float data, and in the shipboard estimates shown here by these two, like the black and the gray, are just different, slightly different estimates of the CO2 flux in the same regions, but based on either the Takahashi 2009 product or the global carbon budget Manchester neural network estimate. Okay, but the point being here that there's a large disagreement in these high latitude regions. And if you look at now the seasonal cycle, so again, these 5 different zones moving from the more northern to the more southern sea ice zone. And now I'm just showing the CO2 flux as a function of months. So this would be the seasonal cycle. You can see that the float-based estimate, which is shown in the solid line with the shading, really diverges from the ship-based estimates, which are the 2 dashed lines. Mostly in this high latitude region, it's in the fall and then the winter. You can see in the summertime, in December here, January, we're actually, the estimates converge pretty well, but it's really in the fall and the winter that you get this large disagreement. And we can kind of, sort of interrogate this a little bit further by combining, instead of just using the float data by themselves, we know that the shipboard data is also giving us very valuable information. So why don't we actually combine the shipboard data and the float data to get sort of our best estimate? And that was what Seth Bushinsky did in this paper that came out in 2019. So this is combining the ship and float data in the Southern Ocean using the neural network method of Lanchitzer. And this is the annual net fluxes now from 2015 to 2017. So you can see that the addition of the float data increases the red area, and particularly, which is the outgassing, sort of the high high PCO2, like high outgassing region. And it's happening in this Antarctic southern zone where you like sort of the high latitude part of the ACC. And it's also particularly, you can see a big change is happening more in the Indian and the Pacific than in the Atlantic. And this is also a seasonal effect. So we can look at this again using the same framework of the neural network method. And if you look at summer months, there's not much of a difference when you add in the float data. So the float data is not really adding too much valuable information in the summer, or too much additional information, but the winter is where you see a big change. And that's not surprising when you think about what the distribution of the shipboard data looks like in the winter. And so if we take that ship and float estimates from Bushinsky et al. In 2019, and we update our picture from Gruber to, the anthropogenic CO2 uptake in the Southern Ocean, we have very independent ways of estimating that. We're pretty confident in our estimate. So we really think that this revised estimate of the contemporary flux what we see with the ship plus float estimate is reflective of a shift in the natural carbon flux in the Southern Ocean. So that really, our best estimate based on the ships and the floats in 2015 to 2017 says that the contemporary flux is a little bit smaller than 1.1, and that again is we believe is due to the natural carbon flux being higher and positive than in maybe previous estimates. And again, this is not surprising if you think about the data distribution. So this is from Amanda Fay's paper in 2018, where she looked at was looking at Drake Passage specifically, but this plot really shows nicely how this is the number of PCO2 observations in SOCAT, E5. Annually, there's a fairly good coverage in the Southern Ocean, but if you just look in June, July, and August, outside of Drake Passage in the Atlantic, the PCO2 observations are very sparse. And if we take the float data now, where we have circumpolar coverage, we separate the float data into the Atlantic sector and the Indian and the Pacific sector. You see a really big difference in these regions. So this plot's a little bit busy, but just to kind of draw your attention to the Antarctic southern zone and the polar frontal zone, and the colored bars are the CO2 flux that you would get if you just use the Atlantic data. And so you see a large uptake of CO2 in the Atlantic polar frontal zone, but a large outgassing of CO2 in the Indian and Pacific polar frontal zone. And then there's also a big difference in the Antarctic southern zone in terms of the total outgassing being much more significant in the Indian and the Pacific than in the Atlantic. And this is, one of the additional valuable things that we get from the float array is that we get subsurface data and co-located, with all with the flux estimates. And so we can look at, we can use that to sort of try to untangle what's causing these differences in these asymmetries between the Atlantic and the Indian and the Pacific. And that's what Channing Prent's done a really nice job of looking at this question using the float data. And this paper's in review, but will hopefully be coming out soon. And just to show you here the seasonal cycle. So now, again, looking at the float data in these two different regions, the Antarctic southern zone here and the polar frontal zone here, and separating it into the Atlantic, the Indian, and the Pacific. The Atlantic's the solid line. So you can see that in the polar frontal zone in particular, there's a very significant difference between the Atlantic sector and the Indian and the Pacific in terms of the CO2 fluxes. So that's really striking, and we're curious about what was causing that difference. Was it due to biology? It doesn't, in Channing's paper, he goes into a lot of detail analysis about this. It doesn't seem to be related to changes in biological production, but instead it's driven, as you can see on these two bottom plots here, by changes in the abduction. So the entrainment of water at the end of the deepening of the mixed layer, this permanent abduction where you get water that's being entrained into the mixed layer from the deepest part of the deepest waters that the mixed layer is accessing. And if you look in at the flux associated with that abduction, you can see very significant differences between the basins. And again, this is all just based on, it's based on float and satellite data. So it's a really powerful aspect of the float data set is that you are getting vertical profiles of this, as well as oxygen and nitrate temperature and salinity. Okay, and I'll stop there, and I just want to sort of put up again my take-home messages to reiterate that biogeochemical Argo floats can improve our estimates of Airsea CO2 fluxes. Although the uncertainties associated with the float-based PCO2 estimates are larger and definitely larger than the shipboard estimates. What you gain by having data, any data, in places where you wouldn't otherwise get it, in times where you wouldn't otherwise get it, is I think is significant. And so we need, I think, to work to reduce the uncertainties in the float-based estimates. And I think the best way to do that at this point seems to be to refine our understanding of how carbon behaves in seawater, and specifically looking at what is SOCOM, what is the SOCOM CO2 based CO2 flux estimates shown us. We've seen that the float data really show a pretty robust signal of outgassing in the high latitude Southern Ocean, and that this signal is really originating from the Indian and the Pacific, and the winter, fall, and I would say fall and winter, and that it's not captured by our existing shipboard data set. And with that, I'll stop and take any questions.
Thank you very much, Alison. That was great. Really appreciated this very thorough overview of what's coming out of the SOCOM project for Airsea Fluxes. Are there questions for Alison? Either orally, you can unmute yourself, or in the chat. And maybe to get things started, I'll just ask, I really appreciated your overview of the uncertainties. I think that's one of the biggest challenges, and certainly something that's at the core of SOFLUX thinking about observing system issues and how to maintain observations. And you mentioned what you thought is needed to reduce uncertainties. I wondered about the role of wind uncertainties.
Mm-hmm. Yeah, no, I think that's a really good point, and it's not something I touched on, mainly because I was trying to highlight just the particular uncertainties that are unique to the float data. But I think that definitely the uncertainties in the winds are, I would say, the next biggest, probably single source of uncertainty in the winds and in the parameterization of the gas transfer velocity. I know that there's been some work looking at the fluxes induced by breaking waves and how that could be really significant, and that's not taken into account in any of the Airsea CO2 flux products that I'm aware of currently. So I think, yeah, there could be, and then of course just the uncertainties in the wind, the wind speeds themselves.
Yeah, those are great points. Other questions for Alison?
Yes, here's Mario Opema from AVI, Germany. So there is a mismatch between, you showed that there is a mismatch between the PCO2s calculated from SOCOM floats and the SOCA data. I think it was about 3 to 4 microatmosphere, right?
Yeah.
So did you account for that, or didn't you? And if you didn't, if you just subtract that value, what would be left of the difference in flux?
Yeah, so I did account for this mean offset because I didn't just subtract that from the data, because especially at this early stage, I felt that this value was a little uncertain. And it's true that if I just subtracted this from the data, it would reduce the mismatch between the floats and the shipboard estimates in the high latitude region, although it would increase the mismatch in the low latitude region. And so I think it's maybe not quite like this, taking this mean offset, I think is not the best approach. But I did account for the fact that that this uncertainty could be is in a potential bias. And so when I did all the uncertainty estimates, like for example, in these error bars are the reason that they're so big is because I'm assuming that when I do a Monte Carlo to get these error estimates, I assume that there's a correlated uncertainty so that all of the floats are off by the same amount. Does that make sense?
Yes, thank you.
Yeah. So I do think it's really important to take into account that fact. And then another thing I'll mention is that when in this study, when we combine the ship data and the float data in the neural network method, you can look at the residuals between what the neural network estimates and what the actual observations were. And we tested out, well, if we subtracted 4 microatmospheres from all of the float data, does that fit the data better? And at least the neural network machinery didn't give a better estimate. I mean, it didn't give a better fit. So in this framework, at least, we couldn't say that the floats were biased or not, if that makes sense.
Other questions? I guess I wanted to also ask you, sort of looking ahead, there's a lot of discussion about potential for other types of observing system for fluxes, sail drone and wave gliders in the Southern Ocean. Where would you put the priorities? Having spent the time looking at these data, what do you think would make a difference in adding to an observing system?
That's a good question. Yeah, I think that I kind of see a biogeochemical float array as being sort of the backbone of an observing system, for many things, and certainly combining with, of course, with the shipboard data. But then in thinking about, sort of new things that are coming online, I do think some things like where you're measuring, I think sail drone is really exciting because you're measuring the winds and the PCO2 in the atmosphere and the PCO2 in the ocean simultaneously. So I think that's something you're not getting, certainly from the floats. And so, some of these surface-based platforms where you really are honing in on the Airsea exchange, I think would be really valuable and could help inform then the estimates that we make with the floats, and kind of help scale up the float and ship-based estimates better. And I think having these, if we think about adding additional vehicles, I think more than or platforms, moorings, whatever they are, more than just what specific platform. I think it's really important to make sure that we're capturing spatially and seasonally the full signal, because if we just put things in Drake Passage, we're not going to really we're going to be missing what's happening, I think, in other parts of the ocean, in the Southern Ocean.
Yeah, that was going to be my next question. How do you configure an array to meet the needs? How many do you need? How does one make those decisions?
Yeah, well,
that's research questions. Maybe.
Yeah, that's a tough question. And I think you have to balance a lot of different questions scientifically, a lot of different constraints logistically and funding, and yeah. I don't know if I have an easy answer, but I think looking at the first step really is to just think about the different scales of variability and what we're going to be, what we need to capture, where, if there are specific regions that are more important, to be monitoring than other regions, how are these, looking at how things are correlated, I think in space and time is really can be a nice can add some quantitative information to the array design, as opposed to a little bit more ad hoc or sort of based on historical data locations.
Yeah.
Yeah, so I think things like SOSI or adjoint based methods where you can look at where adding information, how that affects how that information is propagated, can be really valuable. Yeah, I think also looking at different methods for, this isn't adding to the observing network, but like people are starting to do, I think that paper I showed a plot from earlier from Glogi or something, that where we're looking at the methods we use to take the observations and then reconstruct what it is that we're interested in, because I think having improvements in those methods could gain us just as much as adding several new moorings or instruments out there. So I think looking at the methods we use to make these reconstructions would be also a pretty cheap way of potentially improving our estimates.
Yeah, it's a great plea for being really strategic in what we do.
I had a quick question. Thanks, Alison, for a great talk. It's again about the floats and kind of how they sample, sort of broadening on from the discussion so far. Two things. Would SOCOM not be interested in the future to just have a very small handful of floats sample at high resolution and then be able to more directly assess these uncertainties from the 10 sampling? Even 5 is a real indication of how that looks from a daily cycling to 10 daily. And secondly, is there any indication from the 1990s? Did I cut out?
For me, at least.
Sorry.
Yeah.
Okay, sorry. I hope I'm back.
No.
Okay. The second question, if you can hear me, was about how the floats are Lagrangianly steered in the Southern Ocean, and particularly in strong frontal regions. And that there's some entrainment of floats towards the fronts, and therefore they don't necessarily sample all the high or low EKE areas of the Southern Ocean, in a uniform manner. Is this beyond the signal to noise ratio at the moment to assess these kind of biases on CO2, or maybe are we getting there, or is maybe someone investigating that?
Well, yeah. Okay, great questions. I'll go back to the first one, which was the sampling frequency. Actually, so the SOCOM, some of the early floats did sample at 5 days. So we weren't able to see any big significant difference between 5 days and 10 days. But yeah, I think there's a lot of competing interests in the keeping the sampling at 10 days. And I think although I think everybody in SOCOM recognizes the value of having high frequency observations, the overriding concern is more of maintaining an array that will last a long time, or as long, not have holes in it because the floats have died So I think probably somebody could look a little bit more in detail at the 5 versus 10-day sampling on the existing data. But I think that the real key is to, when you're computing the fluxes from the floats, to make sure that you're using high frequency wind product. It seems that as long as you're using high frequency winds, that the PCO2 is changing on a slow enough time scale. But definitely could be worth further investigation. And then the second question, which I don't know if Seb's still here, but I'll answer it anyway.
I'm here, thanks.
Okay, good. Wait, what was the second question?
The sampling of the float sort of in the frontal regions versus steering.
Yeah, no, that's a really good question. And I think I don't know if anybody's looking at the impact of that on the CO2. Yeah, I think it's, at this point, it is in the below, it's sort of in the noise compared to the uncertainty in the PCO2 estimates and the just spatial sampling. But it would be really interesting to look at that. And I do think, I do know that Lily Dove, who's a grad student at Caltech, is looking at sort of the difference between these high and low EKE regions from float data, but focusing on oxygen, which there you have a lot more oxygen data. So I think could be a bit more promising to tease apart some of those things with the oxygen data set. But yeah, I don't know. I don't think I have a easy answer for what the effect might be.
Nancy Williams has put a comment in the chat saying we are looking at it.
Oh, great. Oh. Well, I can't wait to see what you're finding out. Yeah.
Thanks very much. Thanks, Alison.
Well, we're almost at the top of the hour, so if there are no more questions, thank you very much, Alison. This was great, a really engaging discussion. And,
well, thank you very much. I really enjoyed it, and yeah, thanks again for inviting me.
Yeah, we'll look forward to seeing the next iterations of everything. So we'll see everybody in September for Polar Pod discussion.